So the quantum mechanical model of the atom is our current workings for the electron, the way the electrons are going to function around the nucleus. And so we're going to start off just with a brief recap of where we left off. We're going to try to explain as best we can how you would come up with a model for something you can't see, in this case, electrons. And in the process, we're going to have to learn a little bit about electromagnetic radiation and waves, and then we'll proceed on from there. Recall that we were working with Rutherford's model of the atom, which had a nucleus filled with the protons at that point. Neutrons weren't discovered until 1932. And the electrons were circling around the nucleus like planets around the sun. And again, we want to remember that that's not the case anymore, so just kind of keep that in mind. So the problems with Rutherford's model of the atom basically revolved around the ideas that electrons, being moving charged particles, must always give off energy. So therefore, if those electrons were giving off energy, they would constantly be moving closer to the nucleus and eventually collapse in on the nucleus, and the whole atom would collapse. So this is a real problem with Rutherford's nuclear model. In order to understand more about how the electrons are arranged around the atom, we need to understand a little bit about electromagnetic radiation. Now, the word radiation of itself, usually we get pictures of nuclear radiation, things like that. Well, radiation is quite a large spectrum of types of energy, but they're all basically the same in nature. So you can see from the diagram here that the electromagnetic spectrum includes visible light. Lower in energy than visible light, we have infrared light, microwaves, and radio waves. And then we can go higher in energy than visible light to include ultraviolet, X-rays, and gamma rays, which obviously would be, having more energy are going to be more damaging to tissues and whatever it happens to come up against. So electromagnetic radiation has both wave-like properties as well as particle-like properties. So here we see that range again, and the visible region is a very small part of the electromagnetic spectrum, but it's probably the part that we're most familiar with. The visible region runs from low-energy red all the way up to high-energy violet. You can see, so this chart is kind of flipped around from the chart we had above it. We can see that at the low energy, we have waves that are kind of spread apart more. And we'll talk a little bit about that spreading apart, whereas down toward the higher energy, those waves are much closer together. And we're going to get into learn terms such as wavelength and frequency, in addition to the energy of the waves. So if we take a kind of a blow-up picture of the wavelength is given the symbol lambda, and the wavelength would be the distance per wave. So if we looked at a series of waves here, we could measure the distance between two peaks, or we can measure the distance between two troughs, or any consecutive points on two different waves. The units for wavelength could be centimeters, could be meters, could be nanometers. Nanometer is 10 to the negative 9th meters. So we'll take a look at how to convert from one distance unit to another. The wave amplitude we won't use very much in this course, but you'll see it in physics, will be the distance from the midpoint of the wave to either a peak or a trough. And the frequency is given a symbol mu. And the frequency is the number of waves per amount of time. And if we ever count the number of waves or anything per second, the unit for that would be the hertz, abbreviated Hz. Okay, so anything per second would be a hertz, and that's the frequency. If you imagine yourself standing at the beach and counting the number of the waves that go by your foot per amount of time. That would be the frequency of the waves. The next two properties of the waves that we have are the wave speed and the wave energy. So the wave speed, similar to your speed in a car, the velocity, say, is equal to the distance traveled per amount of time. And if we take a look at our frequency and velocity formulas, remember that the wavelength. The wavelength is the distance per wave, and if we multiply that times the frequency, which is the number of waves per second, waves cancel out, and we get a distance over a time, which is the velocity. So velocity of the waves is equal to the wavelength times frequency. So that's a formula we're going to want to be familiar with. The energy of an electromagnetic wave is equal to a constant times the frequency. So in other words, the frequency is proportional to the energy. As the frequency goes up, the energy goes up. Planck's constant, or the constant H, has a value of 6.63 times 10 to the negative 34 joule seconds. So if we plug in frequency in the number of waves per second, we multiply it times this, we end up with joules for our energy. So we're going to want to do some calculations with this formula as well. The next kind of really important development that happened for us is the wave-particle duality of light. And this is where we end up with H being Planck's constant, is that Planck was able to show that light had both a particle part to it as well as a wave part to it. So it has both wave-like characteristics and particle-like characteristics. And so this is really important in terms of our study of light. Now, how does this factor into our study of the atom? Well, if we put energy into an atom, we can raise the atom up to an excited state. And what we find is that if we take a sample of atoms of a particular element and we add energy to those through heat or through electricity, that those atoms will then come back down to the lower energy state, and in the process will release a photon, which is the particle part to the light, a photon of light. In this case, it's looking at lithium emitting a photon of red light. And what we found is that through the study of adding energy to atoms and seeing what wavelengths of light are given off, we're able to learn a little bit about the energy states of the atom. Now, it turns out that those energy states are really the energy states of the electrons. So we find that there are different energy states or energy levels for the electrons. And then this will get us into then the next topic of conversation, which is the Bohr model of the atom. Just as a kind of an introduction, these are some spectrums that are produced from different elements. So the top one up here is hydrogen, and so you see four very distinct spectral lines that correspond to four very distinct energy levels for the electrons in a hydrogen atom. And so this is telling us that there's a little bit more to the picture than just electrons circling around the nucleus, that the energy, the allowed energy that those electrons can exist at is very specified. And so that's where Bohr took this information, these observations, this experimental data, and came up with his model of the atom, the Bohr model.